Poor thing only does what you ask it to do. All right. So, and I don't know, did I take a picture of it? I don't know if I did. But on the board over here, if I took a picture of it, remember we had, did I do nonpolar on the left? Okay, thanks. So nonpolar. And when I'm talking nonpolar, I'm talking about the whole molecule. And then here is polar molecule. Now, it is very possible, and again, this is kind of a little bit of review, but it's possible for your molecule to have polar bonds, but remember that where the center of positiveness is and the center of negatives kind of annihilate each other. So although there's polarity to the bonds, it's a nonpolar molecule. And so we kind of talk about the net forces of all the net being kind of the combination of all the individual polarities. So that's where that net dipole moment comes from. So if the net dipole moment is not equal to 0, in general it's polar. If your net dipole moment is equal to 0, that means that your center of positiveness and negativeness coincided. So this I'll put centers partial positive and partial negative coincide. It's a spatial thing, right? Centers, partial positive, partial negative, do not coincide. And then remember that your net dipole moment then here is going to be kind of drawn as a vector, or we can do partial positive to partial negative. That's the net dipole moment. Okay. All right. Now, again, this is just looking at carbon bonded to hydrogen somewhere in a molecule. The fact that carbon is more electronegative, we would put it at the tip. Hydrogen less electronegative, so partially positive, partially negative, and that's what you have going on. And so which of these two, carbon, hydrogen, or boron, fluorine, which of the two have a stronger polarity? Just looking at the length of the arrow. This one. Yep. Stronger polarity, length of the arrow. We could look up their electronegativity values and do a subtraction, convince ourselves of that. But that's what you come up with the same thing. When we draw the Lewis structure for carbon dioxide, it ends up being where the central carbon atom is sp orbital hybridized. So it just has 2 sigma bonds and 2 pi bonds, but it's the sigma bonds and lone pair electrons that make the geometry around the atom. I know it's like, that's Chem 1. You're right, that's Chem 1. Okay, so this would be like a non-complete Lewis structure. We can complete it. This irritates you, which it does me, by drawing. There, now they have a complete idea. But the oxygens are more electronegative. So we can draw their individual polarity of their bonds by doing from the carbon partially positive out to the oxygen, carbon out to the oxygen. And so that was, then I have this sort of shape going, where this is my carbon, my oxygen, and oxygen. So we have partial positiveness right there, and the center of these two guys is also right there. So that's what makes it nonpolar. So CO2 is nonpolar, even when we have polar bonds. And then we compare that with water. And water's different. The shape, and I'll go ahead and write it underneath water, but we call that actually the shape of the molecule, which we didn't do in Chem 1. We didn't do molecular shape. But the shape of the molecule for water is bent. And the reason it's bent is because of those lone pair electrons that are extending from that oxygen atom. Okay. So oxygen, hydrogen, hydrogen. Oxygen is what? sp3 orbital hybridized. And so it scatters around oxygen. The geometry around oxygen is tetrahedral, but the shape of the molecule is bent. And so we have partial negativeness, partial positive, partial positive. So center of negativeness is here, center of positiveness is here. So that's why we see, the net dipole moment as like a vector plus to minus. So the net dipole moment is not equal to 0, so this means polar. Now I mentioned on Wednesday that who cares about polarity? Well, we care about polarity. If you've heard like dissolves like, we've actually probably get into that, I'm sure, next week. Polar substances dissolve other polar substances. Non-polar substances dissolve other non-polar substances. The other thing about polarity is what temperature do things melt at, what temperature do things boil at. That's all about polarity, or it can be about polarity. So I think we're getting almost caught up. So I have some molecules here. This is methane. So we have CH4, central carbon atom, and it's kind of similar to water. Central carbon atom, and then we have the the 4 hydrogens, off of that. So the carbon atom is sp3 orbital hybridized. And in this case, I know this gets confusing, I wish there was a better way to do this, but you would say the geometry on the carbon atom hopefully is tetrahedral, and the shape of the molecule is also tetrahedral. Okay. In this case, we have, this is more negative, so center negativeness is here, the center positiveness is also here. It's almost like milkshake. So the centers coincide, so methane is non-polar. But now, if we swap it out, in this case, well, not swapping out, instead we're going CH4, we're going CCl4, also non-polar. Now, if we swap one thing out for something different, in this case, we have 3 chlorines and 1 hydrogen, that changes it up. Okay. So now it may look similar, but the regions of negativeness and positiveness do not coincide. And it gets it kind of hurts my brain, not hurt your brain. But in these cases with carbon and chlorine, we have partially negative, partially negative, partially negative, partially positive, oh my gosh. But in this case between carbon and hydrogen, right, the carbon's partially negative and the hydrogen partially positive. So it's just a really mixed bag here. And you can kind of see how the vectors all kind of work together. Bottom line is your centers of negativeness and positiveness do not coincide. One of the things actually coming up, maybe the next slide, is if you have symmetry, then a lot of times your centers coincide. So this is new. Symmetry, I cannot spell symmetry, I think that's right. If it's symmetrical, like the CH4 and CCl4, that means that there's a good chance your centers are going to coincide. If it's non-symmetric, I think I spelled symmetric right there, but if it's non-symmetric, an example of that was this third compound, the CCl3H, non-symmetric. A lot of times your positiveness and negativeness will not coincide. So if you have a polar molecule, then I just think this is adorable. This could be anything. If you have a polar molecule, you will have a center of you'll have an overall region of positiveness and overall region of negativeness, at least one on that polar molecule. Now, what this is showing you is these are metal plates that we can run a charge through. And if we can electrify these plates, we can make this one over here on the left, the negative means we're going to make it negatively charged, and this plate over here, we can make it positively charged just by running an electrical current. Now here, the current is off. The current is off. Here, the current is on. Isn't that adorable? So here they're random. And here what they've done is to orient themselves. Now, in this case, like is always like, but in this case, the opposite charges will attract. So that's why you see this negative plate. You see the positive ends of the polar molecules leaning this way, and the negative, partially negative parts of the polar molecules over here on the positive plate. I just think that's adorable. Polarity. So polarity is here to stay. So you're going to have some homework that's due, and I got the homework scanned in. It's not on Canvas, but it will be on Canvas before I go. One of the things, Ron, I'm doing differently, I like it, is that, let me know if you have any questions, but all of the homework is already out there on Canvas, so the answer keys are out there. And sometimes students look at me like, you're nuts, Mrs. Snipes. And I like it because that means that you guys can be working your problems, and if you're like, I don't know what to do next, you look at the problem, look at my solutions. Yeah.
When you Canvas, open Canvas, is that a program too?
Canvas? Well, do you remember, it was just last year you were here, wasn't it?
Yeah, it was.
Well, we have something called eCompanion.
Yes.
Yes, it's the same thing as eCompanion, but it's called Canvas.
Campus?
Canvas, like C-A-N-V-A-S.
Okay.
Yeah, we'll have to talk a minute before you go. Okay. So, got sidetracked. Polarity is here to stay. So you're going to have to be able to recognize polarity in a molecule. The only way I know to do that is to be familiar with the way the Lewis structure kind of works out. Okay? So for instance, HF would look like this. Definitely there's, the region of, these can't coincide, can they? Because they're on two different ends. So what do you think? How many people, well, it says polar. It's polar, right? Water, it's a bent molecule, even though the geometry around the oxygen atom is tetrahedral. It's a bent molecule, and that means that's why the centers don't coincide. Ammonia, NH3, is kind of like this. Okay, this is NH3. Where nitrogen, again, has the structural geometry around the nitrogen atom is tetrahedral. It's sp3 orbital hybridized, but we call this pyramidal. Does that look like a pyramid? Again, I guess to get the molecular shape, you just blow off the lone pair electrons that are causing that deflection, in a sense. So that's pyramidal. Okay. So dipole moment, otherwise called the net dipole moment. Okay, and so net is all about kind of adding the different vectors in a way together. We're not going to have to do any calculations, but actually there is a magnitude and a direction to that overall polarity to the molecule. The magnitude can be, you can calculate it by taking the charge, the charge difference between the two times the distance over which the charge is separated. So the charge, the fundamental unit of charge is a coulomb, which we haven't run into that yet. And I put it up here, but we're not going to really dive into it here in Chem 2 either. So if you take that charge times distance, that's why the net dipole moment is coulomb meters, because the distance is meters. The unit of net dipole moment is the debye, and one debye, the symbol for debye is capital D, is equal to 3.34 times 10 to the negative third coulomb meters. And that's a lot of blah, blah, blah. Okay. All right, so back to just looking at something, seeing if it's polar or not. So again, I'm just kind of recapping. If your center of positiveness and center of negativeness coincide, they annihilate each other, and it's nonpolar. If they end up that you actually can see that you have an overall polarity, so you can kind of identify the region of negativeness, the region of positiveness overall, then your molecule is polar. Carbon dioxide, we looked at carbon dioxide before. The shape of the molecule is what we call linear. So this was, and I think I'm just kind of repeating here, this was where the center of positiveness, the center of positiveness is on the carbon atom, and spatially the center of negativeness is also on the carbon atom. So then it's non-polar. Net dipole moment, mu is equal to 0. He's kind of lining up the previous Chem 2 with this unit. Okay, so that was carbon dioxide. This actually has a similar shape to it, but this isn't carbon dioxide. Instead of 2 oxygens, we have an oxygen and a sulfur. So what would you say? Would you say that the bond polarities have the same magnitudes? No, they don't. So if that's the case, you can't say it's symmetric. What would you say? So we have partially positive. Okay, to me the center of positiveness would be over the carbon atom. But what do you think about, because of the lengths of the arrows, would the partial negativeness be here to the left, closer to the oxygen, or would it be to the right, closer to the sulfur? Closer to the oxygen, yep, because it's stronger. Very good. So what you guys just told me is I would draw a net dipole moment, and it would have the plus over the oxygen, and it would have the tip of the arrow going, plus over the carbon. Plus over the carbon, and it would have the tip, maybe if I do this reveal, it's going to show me, isn't it? And it would have the tip going that way. So that would be the net dipole moment.
You can just eyeball it?
Exactly, you eyeball it. Yep. You got it. We're just eyeballing these. Totally. So I've got some more examples coming up. I feel like we've talked about water a lot. So what is the shape, starts letter B, the shape of the water molecule? Bent. Yep. It's bent. And so we said that actually the center of negativeness, I'm going to go with the oxygen atom, and the center of positiveness is going to be between these 2 hydrogens. So that's why I like this figure better than the figure we had earlier, because I just didn't like it. This makes more sense. Partially positive, going up through the oxygen, partially negative, the net dipole moment. And here you see in terms of Debye units, it's 1.85. This was that potentiometric map where the more red hot it is, it's got more electrons. The more blue cool it is, it's got less electrons. This is kind of showing you the little humps for your hydrogens, partially positive, and red for your partially negative oxygen. Water molecule again. So again, in general, molecules that have symmetrical shapes will be nonpolar because their centers of positiveness and negativeness will coincide. And then in contrast, if your molecule is asymmetrical or your molecule is non-symmetrical, then you're not going to get your regions of positiveness and negativeness to coincide. And this asymmetry could come from something bent, like water, or we saw the asymmetry actually could come from something like the CL3H, where you have not the same things attached to them. Okay, so the shape of a molecule. Now, in this exercise, or this first part of Unit 1, we're just going to be dealing with very simple molecules. So very simple molecular shapes. Now, this probably rings a bell. Tetrahedral. Now, this isn't the shape of orbital hybridization. This is the shape of the electron pair geometry. This is the shape of the molecule. So, an example of a tetrahedral molecule would be methane, right? Okay, symmetrical, nonpolar. The other one, trigonoplanar molecule. Remember boron? Oh, city boron. Boron doesn't want 8 electrons, it wants 6. So it does well to do this sort of thing. So picture this with boron with 3 equal things jutting out. Okay. So not only is this probably sp2 orbital hybridized, I wouldn't know until I saw the structure, but also it's trigonoplanar with regard to its molecular shape. And
So it's planar, okay.
yep,
Not
trigonoplanar.
Okay.
And then the last one we've done with like carbon dioxide. Give you an example of that one. Okay, so again, symmetrical, nonpolar. But be careful, these have to be the same. If they're not the same, then their symmetry's off. And that's the case with all of these that we're made. All right. So things that are asymmetrical or non-symmetrical, your centers of positiveness and negatives will not coincide. For instance, water. I'll just go ahead and, this is water. This is your regular water. This is water. Lone pair electrons kind of make this repulsion go on. So yeah, this molecular shape's bent. Pyramidal, remember I said methane is an example, a good example of the NH3. There's methane. It looks like they have a weird bond angle going on. But lone pair electrons here, nitrogen, hydrogen, hydrogen, hydrogen. Lone pair electrons, that's pyramidal. And then linear. And an example of linear that's asymmetrical would be if I was to have something else here. If they weren't equal, that would be asymmetrical. Okay. And then you might be like, well, carbon monoxide, and I think you saw the Lewis structure of it a little bit ago. Carbon monoxide is linear, okay, and definitely it's polar because this is polar, partially negative, partially positive. So here's a table. It might be hard for you to read, but the way it is up here. If we have 1A and 1B joining together, if the two things are different atoms, by golly, you're going to have different electronegativities. You're going to have a net dipole moment, right? So these guys are definitely polar. Why isn't H2 polar? Because it's the same, yep, it's the same atom joined to the same atom. So if you look up their electronegativities, if you take 1 minus the electronegativity difference is 0. Perfect. Over here, we've got we've got 2 different types of atoms, again, 2 different types of elements. In one case, we have 1 atom of one element and 2 atoms of another element. So these all fall in that pattern. H2O, we said, was going to be bent. The geometry, this is molecular geometry over here. The shape of the molecule. Actually, H2S is going to have a similar thing. It's going to be bent. You can see the magnitude of the net dipole moment. SO2 is also bent, but CO2 is linear. And again, that goes back to when you draw the Lewis structure, you have to brush up the dust off those skills. Okay, you'll see that. In this case, we've got 1 atom of one type of element, 3 atoms of another type of element. We've got some examples here. NH3 falls into that category. When we drew that, we have the central nitrogen atom, and it has a lone pair electron that actually kind of repulsed the legs of the 3 hydrogens. So that ends up being pyramidal. Here, NF3 would have a similar pattern, but BF3 actually goes back to, when you draw the Lewis structure, it's going to look like this. Remember, boron it doesn't want 8 electrons, it wants 6. So definitely you're going to have, these would be partially negative, partially negative, partially negative, partially positive. And the centers then, again, annihilate each other. They're in the same location spatially. So just eyeball us. And the last one is one atom of one element, 4 atoms of another element. So we've got different possibilities here. The first one, if all elements, if they're all the same, because that pattern doesn't seem right. Because that would be, anyway, because do you see what I'm saying? Because they should see that B4 should be like a, anyway. So the central atom could be, if it's got 4 things all equal, then notice that there's no net dipole moment. It's nonpolar. If you do some substitution, we have, and actually that's what the 3 there are doing, substituting. Then it is polar, and then down there at the bottom, when you're back to Cl4, it's nonpolar. So y'all okay with that? So these are polar. Oh goodness. And polar. 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 That dipole moment is not 0. Okay. I feel like we already looked at this one. But this was the CCl4. Notice that the region of the center of positiveness on the carbon atom coincide with the center of negativeness, which is also on the carbon atom, because of the way the chlorines are from the carbon. But if we go ahead and substitute from one of the chlorines, we substitute a hydrogen, things get a little complicated. That carbon is actually partially negative with regard to the hydrogen, and it's partially positive with regard to the chlorine atoms. So the centers do not coincide. It's a non-symmetrical. So these 3 compounds are all, again, this kind of reminds me of Chem 1. The carbon, the nitrogen, and the oxygen, the middle atom, has all undergone sp3 orbital hybridization. Remember how that works? Is you count sigma bonds and lone pair electrons. So we have 4 sigma bonds. We have 4 sigma bonds plus 1 lone pair electron. Sorry, 3 sigma bonds plus 1 lone pair electron. 3 plus 1 is 4. Here we have 2 sigma bonds and 2 lone pair electrons. So 2 plus 2 is 4. So that gives us sp3 orbital hybridization. Spatially, these all do 3 different things. Because as we've talked about, what is the shape of, what's the shape of methane? Starts with the letter T. Tetrahedral, yep. What is the shape of the methane? Starts with the letter P. Pyramidal. And how about the shape of the water molecule? Bent. Very good. So which of these is nonpolar? First, second, or third? First one, yep. Nonpolar. Very good. And these other 2 are polar. I don't know what you need to fill in here. This is what you guys just told me. The methane is tetrahedral. The ammonia NH3 is pyramidal, and the water molecule is bent. Again, back to when we're talking about the shape of the molecule. We only deal with simple molecules. Okay. Linear, an example of linear would be carbon dioxide we've been talking about. Polar or nonpolar? Let's see. Nonpolar? I'm liking nonpolar. I'll put NP. NP. Oof, ugly looking NP. Okay. So BF3, do you remember polar or nonpolar? If you go ahead and let those fluorines kind of repulse from the boron as they're gonna, they make that trigonal planar sort of shape. So in this case, that's also nonpolar. Yep, nonpolar. And it's hard for you guys to read up there. I think that says no net dipole moment. So this is mu is equal to 0. Tetrahedral, methane, polar or nonpolar? Nonpolar. Yep. Are all of these nonpolar? Wow. All right, pyramidal. Example of that was our ammonia NH3. Polar or non-polar? Polar. Yep. And I think the hydrogens will be partially positive and the ammonia is partially negative. And then I think, for water I'm going with bent. Polar or non-polar? Polar. Very good. So the region of positiveness is here and the region of negativeness is up there. It's kind of like that. So kind of wrapping things up, but somehow what you need to, for Chem 2 and just for chemistry in general, is to know that it's quite possible to have, I forgot to say, it's quite possible to have like polarity within your molecule, but your overall molecule is nonpolar. Polar bonds, but your molecule is nonpolar. Very possible, happens all the time. CL4 is a good example. Okay. Oh, but that's the next slide. What this says is, I'll do it this way. Structural geometry, I'm going to put Chem 1, CHM175. Structural geometry, that was your SP, SP2, SP3, and you need to know that stuff. I'm not dissing it, because to me, and you're going to see how much you remember from Lewis structures, but to me you have to have a sense of that in order to know the shape around an atom. So that's a player. But that is not the same as what we've just been talking about the bent for water, the pyramidal for NH3. Okay, so structural geometry, electron pair geometry are talking about kind of orbital hybridization, and that actually still has to do with lone pair electrons and all that. But to me, the molecular shape, it basically, I say, you ignore, that's the word, ignore lone pair electrons. That's how you get, I think, molecular shape. Okay. All right. So, do you already say this? Oh, it already says nonpolar. Okay, so just to kind of review, this might help you if you kind of forget. So, that's nonpolar. This guy's nonpolar. This guy's nonpolar. This guy's polar. Okay, this guy's got to be polar. This guy's nonpolar. Seems like I have him up here twice. This guy, you see where it's asymmetrical, so you gotta go with polar. There are different degrees of polarity though. Some are strongly polar, weakly polar, okay? And then this guy, again, these are repeat, non-polar. So this is what I said a minute ago. Don't confuse the polarity of the molecule with the polarity of the bonds. To know, though, what the polarity of the molecule is, you're going to have to take kind of look at this, how the bonds are kind of arranged spatially. Molecule can have polar bonds, but be a non-polar molecule. My favorite example, because there's pretty big difference between carbon and chlorine. When you have that carbon tetrachloride, you get a pretty strong polarity difference. But it's overall non-polar. Okay, go. Yeah, this back-to-back class is like, oh my goodness gracious. So these are posted, and I'll try, I think I got that in Chem 1 last semester, I'll try to do better. I'm giving you one of these for each unit. So, so these, like I said, they're scanned in, and all I gotta do is transfer to Canvas. So I'm close. So part 1 will be due on Monday. And remember, I'm going to do the same thing what I did last semester, is that they're due by 3, and you figure we're done at 1. So if you have last minute questions, you can definitely ask. And I know you guys know this, but if you do, and you guys are really pretty good, if you do use my answer key to kind of help you get unstuck, a few things. One is make sure that you don't rely entirely on my answer key, because then that will leave you hanging for the test when you don't have my answer key. And the other thing is make sure that it looks kind of like what you would do, you know. So change it up a little bit if you can. But in my other class, I did the same thing with my intro students last semester, and they were just like, somebody was just like, you know how you do like a conversion problem, like grams to moles, something like that? They would just write down the answer. Like, are you serious? If you're gonna look myself, at least write down how I worked it. I think you guys are already great about that, you know. So let's go over, like I said, if you don't mind, let's go quick over to the lab and kind of see. Can I just remind you where it is? This is gonna, you guys won't be there